Welcome to the second video in the series of videos on advanced algorithms, and today we'll be talking about dynamic programming and specifically the coin changing example. Using this example we will demonstrate two different versions of a dynamic programming. We'll demonstrate two different thinking processes that lead to two different algorithms. So what is this example? Suppose you are given A dollars, A krona, A euros, and also an array of coin denominations in some country. So it's just an array of numbers from 1 to n such that the first element of the array is the largest denomination in the country, and then the nth, the last element of the array is always equal to 1, so you always have to have a coin of with a value of 1 if you want to change any amount of money. So for example, let's say we have a country where there are only these three coins available. There is a 10 krona coin, 6 krona coin, and 1 krona coin. And let's say we want to change 12 krona. The output of the problem is the smallest number of coins you have to use if you want to change amount A. So as always in these optimization problems, there are two things we want to find. One, and sort of the basic thing that we need to provide, is the value of the variable that we optimize. So in this case, the number of coins. And in this case, we want to minimize the number of coins. Once we have done that, then we may be asked to provide a proof that this is actually possible. So in this case, we're asked to provide a sequence of denominations such that when you sum them up, you get the amount. And so obviously this may not be unique, so you are allowed to use any given denomination as many times as you want. So in this case, how would we change 12 krona using these coins? Sort of the one possible strategy of trying to take as large denominations as possible right away would mean that, okay, let's take 10 krona. Then we are left with 2 krona, and then the only way to change 2 krona is to use two 1 krona coins. So this would give in total three coins, 10, 1, 1. But obviously this is not optimal. So in this case, for this kind of denomination array, the so-called greedy algorithm does not work. We will talk more about greedy algorithms, and in the two videos ahead we will talk about actually a greedy algorithm that for this problem, and we will see when does it work. So in this case it does not work, and in this case the optimal solution is to change the amount as 6 plus 6 using two 6 krona coins. So the answer is C is equal to 2. We have to use 2 coins, and then these are the coins that we have to use. Before we go and develop a solution, a dynamic programming solution for the coin changing example, let's first recall what is the thinking process that you have to go through when designing a dynamic programming algorithm. So the first observation is that you have to start thinking about how to express the optimal value that you need to find, that you want to optimize recursively. So do not think how you are going to construct the optimal solution. In this case, the actual coins that you need to change the amount. Think only about how to express the value. And to do that, you have to sort of think in parallel or in alternating fashion about these two things. One is, what are the local choices we can make when we're giving a problem? So in this case, we're giving some amount to change. What is sort of the first thing we can choose to do? Well, we can choose to take for example, any of the available coins that are available for us, any of the coin denominations. Of course, we cannot choose coin denominations that are larger than the amount we want to change. Otherwise, we have a choice of any of the denominations that we have. So once we make this choice, some choice, in this case, well, let's say I take 10 krona as the first coin. Then what remains is another subproblem, or more generally, subproblems that need to be solved optimally, hopefully. So you have to ask your question, what subproblems are generated if we make some choice, some local choice? In this case, if we make a choice of taking 10 krona coin and we have 12 krona amount, so this means that there remain 2 krona that we have to change. That is the remaining subproblem. In this case, it's just one subproblem that remains to be solved. Sometimes there are more. Then you have to say, okay, so what parameters define a subproblem? And finally, to write down the recursive expression, you need to say what is the base case. When does the recursion stop? So for that, you have to think. So what are the trivial subproblems where we do not, where we know the answer immediately and we don't express it recursively? So the output of this is the recurrence for the value that we want to optimize, recurrence relations for the value that we want to optimize. Once we have done that, then the main part of the algorithm design is completed. We basically got the creative part done. All that remains is technicalities. So what we have to do is first to have a table, or which can be usually an array, one-dimensional array, two-dimensional array, depending on how many subproblems are there and what parameters define those. How many parameters define those. We can have a one-dimensional or two-dimensional array to store the solutions of subproblems. And then from there we can go two ways. Either we can write a memoized algorithm, which is just a recursive algorithm, which avoids solving subproblems, the same subproblems over and over again, but saving them in the table. Another option is to write a bottom-up nested loop algorithm, which is usually in practice a little bit more efficient. And to do that, you have to decide in which order should the subproblems be solved. Because in this algorithm, you want to be sure that when you are solving a specific subproblem, all the subproblems that are necessary to solve this subproblem are already solved. So the order is important here. So now we have an algorithm that hopefully that computes the optimal value, the value that we want to minimize or maximize for a given problem. Once you have that, then you can, as the fourth step, augment the algorithm so that it fills another table, additional table, let's call it T, which is a table of choices, which for every subproblem records what is the choice, the optimal local choice that one needs to make to arrive at an optimal solution. So this table has the same size as the table of solutions to subproblems, and you fill it by just adding some lines in the original algorithm to record these choices. Once you have done that, then you can write an algorithm that traverses this table, usually sort of backwards, constructing an optimal solution. So let's see how this works on the example of coin changing. So for the coin changing example, we want to write a recurrence for the minimum number of coins that are needed to change some given amount. So to do that, we have to think, what is immediate choice I can make when trying to change a given amount of coins? Well, the choice is to choose one of the available coins, one of the available denominations of coins that I have. So let's try to express this in terms of a recurrence. And once we choose some denomination, it means that we reduce the amount by that denomination. And we have another amount of to change. But everything else remains the same about the problem, only the amount changes. So it seems that in this case, the parameter that defines a subproblem is very simple. It's just an amount that we need to change. Everything else about the problems is the same for all different subproblems. So we have all the denominations available. Here is the suggested recurrence for this problem. The minimum number of coins that I need to change a given amount A is defined as minimum. So we take the minimum over all possibilities of all possible choices that I can make in a given situation. So I look at all the denominations in the denominations array which I can use for this amount. So I can use all the coins that have smaller value than A. So among all such coins, I try each of the coins. What does it mean? It means that I take the coin and I reduce the amount that I have to change by the value of that coin. And so now I have a new subproblem for me. So I count one, meaning I took one coin, I used one coin, I need one coin, and then I ask, so what is an optimal number of coins that I needed to change the remaining amount? And I take the minimum over all possible choices in this situation. So this is the brute force nature of dynamic programming. It considers all possible choices in a given situation, solves all of them, and takes the one that gives the best result. How then we end this recursion? In this case, it's very simple. Obviously, if the amount is 0, I need 0 coins to change it. Now you may stop the video and try to think about what is the size of the table of solutions to subproblems that we need to have in the algorithm. So what will be the space complexity of the resulting algorithm, and what will be the time complexity of the resulting algorithm from this recurrence. Try to think about that. So once we have a recurrence for the problem, we can think about designing an algorithm. In this case, we'll design a bottom-up nested loop algorithm. First, we allocate a table to store solutions to subproblems. So for that, we have to ask how many subproblems do we have. In this case, the subproblem parameter is the amount that we need to change. And this can be anything from 0 to capital A, the parameter of the problem. So we create a one-dimensional array which stores capital A plus 1 subproblem. This one is a trivial subproblem of changing 0 krona. Then we have to ask a question, in which order do we have to fill this table so that when we are solving a given subproblem, we already have all the subproblems that we need solved. So for that, we look at our recurrence and see that when we are solving the subproblem identified by a parameter A, we need subproblems with identified by smaller parameters, A minus something positive. So this means that when we are solving something here in the middle of the table, we need only subproblems that have smaller values of the amount to change. So if we fill the table from left to right, from small values of A towards large values of A, we should be doing fine. So here is one way to write this up as a bottom-up dynamic programming algorithm. We have a procedure called coin change 1, because we'll have a different version of it. We'll call it coin change 2. And it has as a parameter A, the amount to change, and the denomination arrays where the first element in the array is the largest denomination, coin denomination that we have, and nth denomination is always equal to 1, if you remember from the definition of the problem. First, in these kind of bottom-up algorithms, first we fill out the solutions of trivial subproblems. In this case, we have only one such trivial subproblem, which is to change 0 coins and 0 krona. And to do that, we need 0 coins. Then, as we already discussed, fill the table from left to right, so from A equals to 1 to small a equals capital A. And we just program this min choice here. So we say we start with some value of infinity for variable C sub, some very large value, and then whenever we see something smaller than that, we will update that right here. And we look at all the possible choices of denominations that we could use in this situation. We start from the smallest ones. So the smallest ones are at the end here, when I equals n, and the denomination of n is 1. And we just loop through all the possible choices of denominations until we go through all of the array denominations array, or we see a denomination which is too large. We cannot use it for a small amount. Then we stop. So if we see this value smaller than what we have seen so far, we remember it. So after this loop, we have found the smallest value of this format in C sub. And at the end, we assign to the value of CA, we assign C sub plus 1. So the smallest of these plus this one. So I move this one out of the min loop here. And at the end, we return that value. So here we have an algorithm that computes the optimal value. In this case, the minimum number of coins that we need to change a given amount. What is the complexity of this algorithm? If you have not thought about that yet, you can pause the video and think about that. So to analyze the complexity of the algorithm, we have to think, we can always think in these terms. First, how many subproblems do we have? So how many iterations of the outer loop? In this case, it's capital A. And then inside, how many choices do we have to consider to solve each subproblem? In this case, it's at most n. That's how many denominations we have. Sometimes fewer if this amount is very small, but in the worst case, we have to run through all the denominations that we have. So in this case, the analysis is quite simple. The answer is that the running time of this algorithm is big theta of A times n. That's the complexity of this algorithm. Once we have an algorithm to compute the optimal value of the variable that we want to optimize, we can augment the algorithm usually in quite a simple manner by adding some lines to remember the choices that lead to this optimal value. And this will enable us later to construct the actual solution that corresponds to the optimal value that we found. So in this case, we just have to remember whenever we see some choice that gives us a better solution to a subproblem, we want to remember that choice. So in this case, we see that this denomination gives better choice that we have seen so far. So we add a line that remembers the choices. So in this case, TA is equal to the value of the denomination that we have just chosen. In this case, so after this while loop completes, we will have in TA the best denomination that you need to take if you want to change amount small a with as few coins as possible. And so at the end, we also return this T. So that is the fourth step in our algorithm roadmap. Finally, once we have our choices recorded in table T, we can write a simple procedure to print out the coins that we need to use to change the amount A. This is the T returned from the coin change 1 algorithm. And we just trace the choices back. We start with the amount small a equals capital A, and while we have some krona to change, we know which coins to use, because in this table we recorded what is an optimal choice of coin specifically for this amount. So we print that coin and we subtract the value of that coin from the amount. And we do that while we still have more than 0 krona to change. So that is one way to design this dynamic programming algorithm. Try to run now the algorithm on the example of from the beginning of the video, where we have 12 krona and denominations 10, 6, and 1. Try to run it on that example. In the next video, we will look at a different way of thinking about the same problem and designing a different dynamic programming algorithm, and we will see how that compares to this version of the algorithm.